Learn the best practices for writing Kubernetes operators using Kubebuilder. This includes strategies for managing multiple controllers for parallelism, resolving conflicts for custom resource updates, implementing efficient retries, and avoiding infinite reconciliation loops. These resources provide guidance on scaling operations to support significantly more users effectively.
I usually start with a problem statement in my videos, but this time I want to do something different. Let's first learn a concept and then we will go to a problem statement and then we will see what we need to do. So let me show you something really quickly. I have a cluster here, and I do have my EC2 instance with a certain spec like this. So this is something we have seen in the video where we talked about how to implement the status update, how do you work with a generation, how do you work with spec. It's just a continuation of that. I will put the link of the video in the description. Now, what happens is, what I wanted to show you is every time you make changes to a resource, the generation changes if you have made changes in the spec, and also every resource in Kubernetes has this thing called a resource version. This resource version is how etcd knows about your object. This is how it is reflected in the etcd. And this is going to change irrespective of whether you updated your spec, whether you updated your label, you updated your annotations, you put any changes in your object, whether it is spec or anywhere. This is going to be changed. Whether the generation will only be changed when you actually update um, the spec of your operator or of your resource. So let's do some changes here. I'm going to say testing, and this is a change. Now, if I save and quit this, you see what happened? We went from generation 4 to 5, and there was a different number for the resource version. Now, to show you something that it does not really matter what change was there on on the object, if I just make a new label and I would say cloud GCP. Now, this is to show you that we are not making any changes on the spec, but rather a metadata change. But even that, if I save and quit, you see, this changed. The resource version did change. It did not change the generation because we didn't make changes to the spec of our object, but the resource version changed. Just to quickly show you something else, environment, and I would say production. Now, right now, the resource version is 42331, but if I save and continue, that's going to change to something else, and it is 42345. And that's something I wanted to show you. It does not matter where you make what change in your object. If it has changed, it's going to get a new, the change is going to be committed to etcd, and every commit is going to have a new resource version. So now that out of the way, let's move to the problem which I was facing and that got me to record this video. Um, Now imagine this is what you were doing, and this is something what I did. I felt the problem, and imagine this is what you are also doing. So you have a requirement. Let's start with it now. You have a requirement where you want to make an operator, right? You want to make an operator that is going to work, and that's eventually going to give you a VM running somewhere. It could be in Amazon, it could be in GCP, it doesn't really matter. What this VM is going to do is eventually this virtual machine is going to be added in your cluster as a worker. So think of this as you're making a scaler, you're building your own custom auto scaler. And this is something what I felt when I was working on a similar project. Now, when you are writing an operator, you know you will be writing some custom resources, And for that, you will be needing some custom resource definitions. So when I was working on it, I decided my custom resource definition to very simply look like this. So the kind was a node pool, and this will define the number of nodes that I can have. So a node pool resource would be defining how many maximum nodes can I get, what is my target node, what's the name of my node pool, and also a very simple configuration like how big the node should be, how much disk do I need, and how much memory um, am I gonna need in that particular node pool. You can think of this node pool is going to create me a node which is going to be in one of the cloud providers somewhere, and that is going to be then registered in my cluster. The thing is, a node pool can be created manually. When I create this custom resource, let's say I have built my operator. My operator has the knowledge of creating a virtual machine. My operator has the knowledge of registering that into my cluster. Now, if you really want to start using it, when you create this custom resource, you can make changes on these target nodes. You could say from 0 to 1, and your operator is reacting on that change. So what it sees is, it sees right now I've got like 0. Let me change to a different color. Right now I've got 0 nodes of this configuration. The user has asked me to create one node, and I'm going to go and I will give them a node. This is what a very simple operator that you wrote. You also have not just this spec here, but you also decided to give a status of to someone who is looking at your node pool. So this status has a key called scale operation, and this is usually inactive if your operator is not doing anything, which means if your operator is not busy creating a node or registering that to the cluster, it doesn't change from inactive. However, this scale operation changes. This scale operation changes when when you are actively creating a VM in a cloud provider from inactive to active. And this is what you wrote an operator for. This is something similar to what we did in my Kubernetes video of how to build your own operator that manages EC2 instances, similar to what I was working on a project in my company. The thing is, you were able to create these resources manually, which is a node, because you have an operator, you deploy or you create this custom resource. Based on the custom resource, your operator runs and it creates you a node, and everything is happy and healthy. However, you decided to take this thing one step further. You said that instead of me deploying the custom resource and then I do kubectl edit node pool, and then I will go from 1 and change this to 2 and save and quit, and eventually there goes another node. This was node number 1, this was node number 2. I don't want to do this. This is a scalar. This is not an auto scalar. So what you decided was that this kubectl edit node pool, or in the end, the increment to this target node, this target node should actually happen on a certain event. And you decided that this event should be a pod being in a pending state because of CPU or memory. Now, you know that a pod could be in a pending state for so many reasons. The pod could be in a pending state because there is no secret that the pod is referencing to, or a persistent volume is not available that the pod needs. The thing is, you have the logic where you list on all the pending pods, you find the ones which are actually pending, because of CPU or because of memory, you see, if the memory that the pod is asking for, let's say, if the pod is asking for memory which is around 28 gigabytes, um, and then you have the logic that yes, because the pod is asking for memory that is less than this 96 gigabyte, if I create a node, the node will be enough for my pod to be deployed. You wanted to have this trigger, so you have this as an autoscaler. Now, what you do for all this, let me quickly go and delete this because we don't need it. What you decided was that I'm gonna write another controller. So there are two controllers right now which are working in your operator. I think it makes more sense. Let me just quickly say you can have one single operator which can have multiple custom resource definitions, and also multiple controllers there. So you said, right now, I have one custom resource definition, which is called a node pool, and there is an operator that reacts on top of that, and that's going to be the node pool operator, which is eventually the one that creates you a virtual machine or a VM, somewhere in the cloud. You then decided, because you wanted to make this an autoscaler, you say, I'm going to have a new custom resource definition, and that's called an autoscaler. Let's say you create a new custom resource definition and you name this as autoscaler, and then there is a autoscaler autoscaler operator. This autoscaler custom resource is very simple. It just says how many, or how long to wait before checking for pending pods. Let's say frequency, for example. You can say that my autoscaler operator should look for pods every 5 minutes. This is the frequency that you are configuring in your custom resource definition. So this might look something like, let me just quickly go and write a YAML for this. This would make more sense. So your kind will be auto scaler version 1. Then we have the metadata. Wait, am I doing something wrong here? Let me quickly just get the API version and kind and metadata. So this is what I was missing, because every resource needs this. So I have my API version as compute.example.com v1. Kind is autoscaler, and then we have the metadata, the name my autoscaler, and then you could have a spec. Essentially, when you are working with Kubebuilder, you create the spec, you define the spec of your custom resource. In this case, I would have the list of namespaces to target. These are my prod namespace. Then I have my search namespace, and then I have my real money maker namespace. These are the namespaces in which I want to target. If there is a pending pod in these namespaces, then only I want to scale. Because there could be people creating dev projects, and I don't really want to care about if there's a pending pod because of CPU or memory in the dev project. But if these projects are there that have a pending pod, we want to be creating or reacting on that event. Then you could say frequency, and you can say 5 minutes. So every 5 minutes, your autoscaler controller will check the pending pods in the list of namespaces to target, and it will react on top of that. That's simple. So you decided then I'm going to write these two custom resources, and I'm going to write these two different operators. This operator creates the VM. This second operator just finds the pending pod. It just finds the pending pods. Now, because what would you want to do if you have found a pending pod? You would want to create a VM, right? Because there's a pod pending, you need compute, and you would want to create a VM. The thing here to notice is many times you might find yourself in a situation where you have custom resources, you have multiple operators, and they talk to each other's custom resource, not just their own, but each other's resource. In this case, for example, the autoscaler operator, once it has found some pods, what this would do is it rather than this creating a virtual machine, it updates the custom resource called node pool. Essentially, think of this as kubectl edit node pool, and then you update the number of target nodes. Let's say whatever the number was, 2, you change this to 3. And because you update the custom resource called node pool, the node pool controller will see this change and it will eventually create you a VM, and then your VM will be registered as a worker. The thing here to understand is a different operator, which is our autoscaler operator, is using a different custom resource. This is not, only working on its own custom resource definition. And you will find this happening a lot. And that's where things get interesting. So let's draw a timeline on what actually happened. So you start from the very beginning. Uh, Imagine a cluster where you have your operator, your resources all running. Now, what you do is you install or you create a YAML for the node pool, which is essentially something like this, which we already have here. So I'm going to go copy this and let's paste it over here. Oh, okay, that was something I was expecting. Let me clear that so this becomes a bit more easier to work with. Should have copied this somewhere. Okay, so let me quickly just copy that and keep a fresh copy of this in case I need it in the future. So see what happened. You created a node pool. You created a node pool resource here, and you define the target nodes as not 0, but you define the target node as 1. Or let's say it's 0. To begin with, it is 0. All right. So you're not doing anything. You just say, I want the resource to be there in my cluster. I don't want it to do anything, but let's let it be there. And let me quickly go ahead and get this here. I think we can just get from carbon.now.sh here. This is my YAML. I'm going to copy this image, and here is my custom resource definition, or rather the custom resource for the autoscaler. So these are two CRs that you have created. I hope this is making, this is going to be clear. The two custom resources, eventually, because you have two custom resources, you also have two operators. But the operators are not doing anything. So the reason why they are not doing anything, for this one, you have the node pool operator. For this one, you have the auto scaling operator. They're not doing anything because first, your target node is 0, so nothing needs to be done. And also because you don't have any pending pods in these namespaces, so nothing is being done. Now, let's say you manually went, and you said that I'm going to create one new node from the node pool operator. what you do, the first thing you go ahead and you do is kubectl create, kubectl say edit my node pool, which is a short form NP, and you change this target node from, you change this target node from 0 to 1. All good. This operator starts working. It is working. And because you made a change, in the spec, a new version would be there, a new, for the same object, the generation is going to change from 1 to 2. And this is also going to be updated to a number X, Y, Z. That's all good. This would be updated. Now, coincidentally, while this operator is doing its job, you found a pod which was pending in the prod namespace. See what happens. You found a pod which was pending in the prod namespace, and you have configured your autoscaler operator that if pending is found, you're going to update the custom resource. You're going to update the custom resource, which is in this case the node pool. So if you found a pending pod, you update the custom resource, and this is same what you're doing. Kubectl edit node pool. Kubectl edit node pool. Keep this in mind that this all happened while your operator was working. While your operator was working. Now, what you do is you edit the node pool. Now, this is going to move from 1 to 2 because from 0 to 1 was you did this manually, kubectl edit node pool, and from 1 to 2 was done by this particular operator while this was running. Okay, while this was running. Now, what's going to happen? Not just the target node is changed, but the generation also changes 3. And this goes from XYZ to ABC. Okay. And this is all done. It's done. It's working. Once this operator will finish, you might want to update this custom resource back, because when you start working, you change this from inactive to active because your operator was running. And when the operator is done creating a virtual machine, registering that to your worker, to your cluster, you might want to update the object from active back to inactive because it's not technically doing anything. And that's where you're going to have a problem. That's where you're going to have an issue. See, when your node pool operator started, every time, and this is how it's going to make more sense. Let's say you have a custom resource. Its resource version is 1, and you start an operator based on this custom resource with the resource version of 1. Every time your operator sees that there was a change on my custom resource, the first thing it does is it downloads or it caches the object. So if your custom resource had resource version 1 in HCD, here as well, your operator knows that the version latest is 1. And the operator starts doing its work, whatever it is doing. Now, someone or you or another operator, another controller, it updates this particular custom resource. And this changes from 1 to 2. Your operator still thinks that the latest version is 1 because it hasn't gone to HCD to get the latest copy. It didn't know that the operator version has changed. It doesn't even have an idea about it yet because it's still running. So while your operator has an older version of the resource, you went ahead and you updated this custom resource in HCD. Now the resource version is 2. Now, when your operator is done, and usually you might want to update the object. Imagine this was a custom resource for the EC2 instance use case that we have been talking about. Now you got the spec, the resource version was 1, you create the VM, you got the public IP. Maybe you want to add the public IP in the status of that object, because every object has spec and then the status. You want to update the public IP in the status. You try to update the object for which the resource version of the object was still 1. And that's where the problem happens, because when you try to update the object, you essentially want to commit into HCD. So you are telling HCD that, hey DCD or hey HCD, I want you to update an object whose name is so and so and so. HCD doesn't care about the name, it cares about the resource version. So you are saying, update the object with a resource version 1. And HCD says, there is no such object whose resource version is 1. I have some whose resource version is 2. So it looks like you either have an older copy of the object or you are clearly doing something wrong. And that's what you need to fix. And this is the problem that happens when you are working with more than one controllers, where each controller is, touching a different custom resource. And this is called a conflict. You might have seen this error at some places. You might have seen this, that the object that you are trying is old, get the latest copy of that object. So essentially, if you really want to update this object, what you would do is, before writing to HCD, because your object update has failed, what you technically do, you get the newer copy from HCD. You get the newer copy from HCD, and now your resource version is 2. And then you will then update, you will retry the update object um, task, or you will try to update the object again. And this time, because you are making a change in HCD for that object, its resource version will now change from 2 to 3. See, anytime anyone makes any changes, you're going to have a new resource version. When you create the resource for the first time, let's say the resource version was 1, and that's what your operator started with. Now, this guy made some changes to the resource version went to 2. So you try to update on an older version, where in HCD there was a newer version, it failed. You fetch the new copy, and then you try to update. And because the last resource version was 2 and you are doing an update, this changes to 3. And that is the whole story of me trying to explain and come up with this situation. I hope this has made some sense. If not, the comment section is open. You can always ask these questions. But this problem that can happen to you, and this happens because you're trying to update an older version of the object, where the object has already been updated by someone external, but your operator did not know about this. So to fix this, there are two different ways in which you can, fix this problem. The first way is a simple way, or I like to call that a lazy way of doing it. And the second one is a pro way of doing that. Now, it doesn't make sense for me to talk about the simple or lazy or pro, but rather let's go into the code and let's see what different ways are there where you can make your operator intelligent, that, okay, the object that I'm trying to create, it has been updated by someone else somewhere. Let me get a new copy, and then I will try to make my changes on the new copy. So let's go into the code, and then let's see that how it works. All right. So if you look at the code here, let me just quickly walk you through how we are building our API. And in this case, I have a very simple API custom resource type, which is called EC2Instance. This is something that I always use in all of my examples. So if you are working on this best practices series, you already would be very familiar with how do you build an operator, and there's a whole course on Cube Simplify of how do you build this on scratch. We'll probably put the link in the description here. And here you can see I have a very simple custom resource called foo and bar. It has a spec, which is just foo and bar, and this is just a very simple string. Look at the operator. This reconcile function is the main function that runs whenever you make changes to your custom resources. This is the one that tells you what to do. Here's a bit of a fancy print statement, so we can see in the logs of when the reconcile is started from the beginning, and we get the object that is being worked upon into a variable of type EC2Instance. Now, every object that you have, it has a spec, it has a status. That is something you can define in here. For my case, the spec just contains foo and it contains bar, which is another uh, key in my object. However, every object gets some metadata. So every object would have a UID. Every object would have some labels that you do not set in the beginning. This is something which is coming from the Kubernetes API server. Similar to that, every object has a generation and a resource version. So while the resource version, think of this as the version of the object in etcd, and the object generation is the resource, it's a deployment version of the object. So when you create the object for the first time, its generation will be 1. Any change in the spec that you make increments the generation, and that's how you can know what is the old version and what is a newer version that is being worked upon. Now, in this function, which is a reconcile function, it's fairly simple. I'm just trying to simulate a time-taking task that would be done. Usually, your operator, which is in case the EC2 operator in here, it is supposed to be creating an EC2 instance on Amazon. So usually this would go to AWS, make API calls using the SDK written in Golang for AWS. It will authenticate to Amazon. It will give the information that I want to create an EC2 instance with this name, the security group. It should have these tags, these labels, this is the AMI ID, all of this information. And eventually, you're going to get back some response from Amazon. This is something we already talked about in the course for building operators from scratch. But I'm not doing this all. In here, I'm just counting from 1 to 10, and I'm printing. I'm doing a task and the number of the task, and I'm sleeping. Time dot sleep. Now, this is where the fun part begins. See, while you are working in your operator, while the reconcile function is running, see what happens. There's an object, right? There's an object. Let's say you just create this object. Its generation would be 1 because it is just created, and its resource version would be some random number which is given by the Cube API server. Now, your object was created, and the operator fetches this object and it stores it into the cache of the object. And this is what's being done here. So this is the part which stores the object into the cache of the reconciler, right? You start and you make some changes. Now the operator runs and it keeps on making the changes. However, what we discussed is that you can have multiple operators trying to write on the same resource. So there could be another operator or a human that goes and does kubectl edit EC2 instance, and it goes ahead and probably change some aspects of the custom resource. Now, when you save and quit, when you save and quit your changes, the version is going to be, the generation is going to be from 1 to 2. Here, the old object is with generation 1 and it's XYZ, and this one's going to be A, B, C, and the old object is generation 1 XYZ resource version. This one is generation 2 and ABC resource version. Now, what happens? Your operator is going to make a change. Maybe it's going to update the spec, or maybe it's going to update the status. Let's put it this way. Your call to AWS to create an instance gives you a public IP. Maybe you want to put this public IP in the object status. But this is where your operator is going to cry about. When you say that update, when you run the update function or you make the update call, what you're telling to Kubernetes that I want to put this update onto an object whose resource version is XYZ and its generation is 1, because that's what you are aware of. Your operator does not know that a change has been done outside of its scope. It doesn't know that. And when it goes to do it here, when you try to do an update, you get an error. It says the object that you're trying to talk about no longer exists. I don't have an object with this resource version or this generation. There's a newer object. There's a change in that object that you do not know about. And this is where it gets interesting. So see what's happening here. We try to run some steps in the operator, try to run some steps, and I have a very simple scanln, so I can wait. This is going to run and let me make my changes outside of the operator with kubectl edit. So this would be similar to what any other another operator would make changes to the same object, and until I press enter, this just gives me a little bit of a time. Until I press enter, it will not move ahead. So when I do enter, what's going to happen is I'm updating my spec.bar to a new string or to a different string. And when I try to update, this is where it's going to fail, because I have already made changes to my object outside. The version has changed. The version that operator knows right now is the old one. And this is where it's going to be a problem. Now, if any error happens in your operator, you usually want to retry that. You usually want to retry this. So this is where the return function comes into the picture. The reconcile, this reconcile function, it has two return types, or it returns two values. One is the result. The other one that we are more concerned about, and this is the lazy way of doing things, is the error. So when you have a reconciler, see, the way it works is when you have a reconcile function, if it's going to return an error, if the error that is returned is not nil, Kubernetes is going to see, okay, the reconciler wanted to do something, but it could not do that because, and that is why it returned an error. I would try to run this reconciler on the object again. And this is the self-healing mechanism of Kubernetes. Maybe you could not create the Amazon instance because there was a network problem, and when your reconciler exits, it says the work hasn't been done. Kubernetes will try that again, and this time the network calls would go through, or maybe you had some permission issues and you fix the permissions, and this is how the self-healing works with Kubernetes. In our case, if we could not update the status, the custom resource, it's going to return an error. And this is the lazy way. The reason why, if there's no error, don't return anything. The work has already been done. We don't return anything. If nothing is returned, the reconciler does not run again. It just waits for a new change to an object that it is responsible for. But see what would happen. Because we will not be able to update, there's an error. The reconciler will run again from the beginning, and it will go through all these 10 tasks. It will go through printing the object and the resource version, but this time it's going to get the newer version, because it's this get object, this get function gets the latest object that is being worked upon. And this time it's going to be version 2, which is some change that was made outside the operator. And this time it's going to get the object, print the version which is new this time, and run through all the steps of your operator, which it should not be doing. There's no reason for doing that. But because you returned an error, it says, I'm going to run through everything in the reconciler. And this is why I have been saying that your reconciler need to be idempotent. If no changes are required, to be made, no changes should be made by the reconciler. Now this time, everything will be fine. And because there's the same version of the same generation and resource version, because you get the latest one that is available, you would be able to update the spec. You would be able to update the spec, and without any errors, you will be returning a nil. And that's the lazy way, because you run your reconciler loop again just to get the new version. You're spending compute cycles, you're spending a lot of time, you're running your reconciler, you're wasting your compute capacity for no reason. Instead of managing the error here itself, you return the error, you let Kubernetes run your reconciler again, get the new version, and eventually move on with the update. And this is what I want to show you. Now, before I can show you, I also want to talk about, I have changed my development environment. Before I was using Kind, but now I'm using Wind, or Wind as some people would call that, which is vCluster in Docker. And that is going to be the base of every operator that I build, every development environment that I ever would be needing. Wind is really, really cool, and it gives you a lot of functionality, which I'm sure there are other videos on Cube Simplify which you can look at. But for a very simple example, you could just do vcluster create, and it's going to give you a vcluster in Docker. So exactly drop-in replacement for Kind. And I have my vcluster.yaml file, which if I can show you, it looks something like this. So I'm going to get my worker nodes as the Docker container. Wind also gives me flexibility to create an Amazon EC2 instance and attach that to my local Wind cluster. I'm going to be deploying the default Flannel Flannel CNI, and the Kubernetes version that I'm using is 1.3.4. And you can do vcluster create the name of the cluster. In my case, this is Retry. The driver would be Docker, and this works very well on Mac with ObsStack. In case you're using this, you can totally use that. I already have this cluster running from Wind, and you can see I've got these containers, and this is where my Kubernetes cluster is running. So we have a working Kubernetes cluster. We also need our custom resource definitions installed on the cluster. And because we are using Kubebuilder, and this is a make file, it has some make targets, make manifest, make generate, and make install. What this is going to do is it's going to create the CRD. It's going to apply them on my cluster, and I would be able to do kget ec2 instances, because this was my custom resource definition, or rather explain ec2 instances. And here you can see it knows about this particular resource. And if I do spec, you will see the foo and the bar examples here. And this is the spec that I wanted to do. Now let me quickly show you this in demo, and let me run my let me see, I should be empty. Okay, good. I'm running my main.go, and this is running the operator on the V cluster in Docker. Now see what happens. As soon as I create an object of type EC2 instance, let me just quickly show you how does it look like. So it would be config examples, or config samples compute. This is my EC2 instance, which I am creating, right? So let's do that. If I do create, what's going to happen is my reconciler is started on the left side. You can see the generation is 1 because it's the first time this has been created, and the resource version is something different over here, right? The resource version is something different over here. However, it looks like it should be stopping. Probably. Oh, yes. So what happened? This was supposed to stop here so that I could go ahead and make the changes myself. But because I hit an enter, it was given as an input and nothing waited for me. It just moved ahead. But let me quickly do a delete. And then let's rerun this again. So this time I'm going to make sure I do not give any enter. I want this to wait for me so I can make changes myself to the object from outside the operator. So if I do a create, now see what happens? If I do get EC2 instances hyphen YAML, this is the generation, and that's the same generation my operator knows about. So that's good. That's perfect. And the resource version also is what it knows. So right now, both of them are knowing the same object. But what I'm going to do is I'm going to edit my EC2 instance, and I'm going to say this change is made while the operator was working on the resource, something like that. Now it's edited, and if you look at this again, this time the generation is incremented by 1, and also the resource version is changed. This tells you that Kubernetes or API server or etcd sees this object differently than what my operator holds here right now. Now, when I press enter, what's going to happen is it will be at this stage. When I press enter, it will try to update my bar. It will change whatever string is there right now for bar, which is testing. It will replace it with this string comes from operator, and when this tries to update, it's going to fail. So let's press enter, and now we will see. Now see what happens? This is the problem. It says operation cannot be fulfilled on EC2 instances. EC2 instances, the object has been modified. Please apply your changes to the latest version and try again. Try again. The way you are trying again now, and this is the stack trace of the error, the way you are doing a retry now is that you simply say panic, I'm returning an error. And the way reconciler works is if you return the error, the whole the whole loop would be running again. And this is what you see here. The reconciler started. This time it got the new version, which is version 2, right? It got the resource version, which is resource version here. It ran through all these tasks. It ran through all of these tasks, and eventually it now knows the latest version that there is. And here you can see when I press enter, it did update the object, which is it went through because nobody else updated the object while the controller was running. It did not change the version. This time when you did an update, a new generation was changed, or rather a new generation was incremented, which is you see here. Any change on the spec updates the generation. So when you create the object for the first time, that was the generation. I make the generation 1. I made some changes manually. That incremented the generation 2. And this time, it went to generation 3 because I was able to update my object using using the controller that we are writing right now. This is a lazy way of doing things. However, there's a better way of handling errors so that you don't just simply say, hey, there's an error. You don't do that. Rather, Kubernetes gives you a package called errors. So if I show you go package Kubernetes package errors, and here's this errors package, and this is where Kubernetes has defined or Kubernetes has defined all the errors that you can get. A lot of times you might see problems like unauthorized. Maybe you say it's forbidden, it's a new conflict that you have. This object already exists, so I can't create that. All of these are already defined in the package, in the API, called errors. And this is something that we can use to figure out what type of error it was and what to do on top of that. So let's look at these errors and see how we can make our operator smarter. So instead of quitting and rerunning from the beginning, it gets the latest version here itself. When it fails to update, it says, okay, looks like the operator outside, looks like the object outside has been changed. And let me quickly go and get the latest version right here instead of running the reconciler all again. So let's take a look and see how this is done. All right. So what we're looking into in here is to try to update our object if there was a error. We want to retry if there was an error trying to update our custom resource because the version has been updated or modified somewhere external to our operator. The first thing we need to know is how can we find out what was the error? So this update function here, it does return an error, but it is on you to control that error. It is on you to define how or what that error was. It could be that the object was no longer available. It could be that you did not have permission issues or you did not have permission. It could be there was a 500 error that you got. How do you classify these errors that you are getting when you are trying to update the resource? And for that is what we talked about, the error package. You could do if the error is a conflict error. Something like this is how you can say that if I got an error, I'm using the errors package, and if it was a conflict, this error type is already defined by Kubernetes in the errors package. So if I show you that, go package errors, here, you can see this package implements the functionality to classify the error. No, this is not the one. It's for Kubernetes one. This one. So this defines already given scenarios in which you can run into, and you can probably be given an error. For example, you try to make an object which is already available with that name. When you try to do kubectl create on a resource and you try that again, that's what you get returned. And this is what the error is, that it already is available. One of the other one that we're looking into is the is conflict function. It checks that the error that you got when you're trying to update your object, if it was indeed conflict issue. So you print out that the conflict error was there. Maybe you would want to send an email to the team that, hey, I tried to run my operator and I tried to run the controller, and when I tried to update my object, there was an error. Or you might want to handle it here, right? You might have another errors as well. So it's not the only reason that you could not update the object, uh, could be because of conflict. It might as well be that the object you are trying to work on, it has been deleted from from Kubernetes itself. So when you try to update that object which no longer exists, you're going to get an error. And again, here we can see if errors is not found, something like this. And here is how you can make here's how you can make your operator more smarter in terms of how to do error handling, how to do error management. In our case, if there is a conflict, we want to retry. We don't want to quit the reconciler. We don't want to do that. We want to stop there and retry rather than exiting the reconciler, returning an error, and Kubernetes will see, hey, this operator did not work properly. It is returning me an error. So I'm going to rerun all the steps again just to be able to update the function. Essentially, at this stage, when you got a conflict error, you want to get the new object version and store in the cache, and then you update the object with the new version, right? That's what you want to do. And for that to do, there is a fairly simple function, and there's actually a package that Kubernetes gives you so that you can implement this retry. For without even that, you could do very simply. So it's going to be the same code that I try to get my object, right? If there was an error, let's get that again and let's update. And this would be very, very simple. This is how you can implement an error conflict functionality. However, the thing is, you can again get an error trying to update your object. It's not like you got an error once and the next time it's going to work fine. You might still get an error. You might still get an error here. And in the end, you're doing the same thing. You are trying to just exit the reconciler because you're returning an error because you got an error when trying to update. And it's kind of like you're going into a loop here. So Kubernetes has a retry package, which I can probably show you. Kubernetes Go retry package. It's somewhere around here. It's in the client Go. And you can use these two functions available. So one of them is on error. The other one is retry on conflict, which is something we want to only try if there was a conflict. The first one is pretty generic on any error. You want to try that again. This one we want to try on conflict, and it has certain options to control how do we want to retry. So this is something that we can use. I would say retry error, and I'm going to use the function retry dot return on conflict. You can see I've already got the tab completion. I'm not sure which function or which model am I using, but this is cursor. And let me just quickly do this retry error, and here we go. So this bit makes your retrying a lot more smarter rather than just manually getting, because we are still doing the same. We are getting the object, the new one, from the Kube API server. We try to update. This is exactly what we did even without this function. But what does it give it to you? The one thing that I really like about the retry package, and especially the retry on conflict, is that it does give two inputs to this function. The first one is some default backoff, or it is a set of configuration that tells Kubernetes or tells your reconciler how many times do you want to retry before failing. So if you look on the default backoff, it has steps as 4. That being said, it is going to retry 4 times before giving up and telling to Kubernetes, hey, I tried, I could not update it. So this is kind of like a retry within the retry on conflict function. That's what it gives you. How many times do you want to try again? The duration is the initial time before which your retry function will wait to try for the first time, and then the subsequent times. For example, um, it's 10 milliseconds. So for me, it's going to start at 0 to 10 milliseconds to retry. If it fails again, then take another 10 milliseconds, then another 10, then another 10. So 10, 20, 30, 40 milliseconds is how it's going to be. The factor controls what is going to be your duration, or how effectively you're going to retry. So in this case, the duration and the factor, it's kind of like a multiplier. So if I have a duration of 10 seconds and the factor is 5, for the first time when my operator starts, it's going to try on the 10th millisecond, then on the 50th millisecond, then on the 250 millisecond, then after 1.25 seconds is it going to try. So it's multiplying your duration with the factor, kind of like giving you multiple tries with an exponential back off. Within every try, you're going to stop a little bit more and try again. And this jitter is zero point 0.1 up to 1. That's a maximum value. This gives you the randomness between the time on which you're going to retry your update statement. This is especially useful when you have more than one controllers They all have the same duration. They all start at the same time with the same factor. They all will try to write the object at the same time. And this is something we do not want. So jitter will actually be changing the effective time. So if you would see the duration and factor, this would be something like if your duration is 10 and your factor is, let's say, 5, it would have been, it's going to do 10 milliseconds, then after 50 milliseconds, then after 250 milliseconds, you're multiplying that by the factor. But when you have jitter, which is jitter would be 0 0.1, or it's 10%, that the randomness that you are involving. So it would be 10% of 10 milliseconds. Within that, it's going to start, right? So it's not going to be exactly 10 milliseconds, but it's going to be probably 8 millisecond, 9 millisecond. Then for 50, it would be 47, 48 milliseconds. A randomness is added. So it is not exactly this particular time on which you are retrying. This helps you when you have more than one controllers running at the same time, and they all have the same factor and the same duration. They try to hit your Kube API server at the same time for updates. And this randomness would be allowing them not to do that at one go. So this retry on conflict function, it takes two inputs. One of them is the configuration of your backoff, which is the step and what we talked about. The another one is a function without any inputs, and this returns an error. Essentially, the return on conflict function itself, it returns an error. You can see here in the function definition, this is the error it is returning, and this error comes from this function, which essentially does nothing, but it tries to get the object, right? It gets the object and then tries to update your operator or your custom resource again. You don't have to have this line because it's the same update that you want from the spec that you have changed, and then you try to do an update. You return the error of if there is any, because update function also returns an error. So essentially, we are trying to get and update the resource, and we're returning an error if there is any to the retry error variable here. And this is where we can see this bit goes into a loop for your number of steps. It waits for the randomness. It waits for the duration. Then it goes on every factor and added the randomness. It defines the time for four steps or four retries. This is something you can also very well configure. You can give your own configuration. Maybe you want to try for 8 times before you say, okay, I give up now. There was an error. And despite trying for all these retries, the steps that you have, like in our case, is 4. If it is still not nil, that you can only retry. It's not like it's a guarantee that your update is going to go through, but you are retrying. You tried again, maybe 10 times you tried, and here you can say print ln I tried 4 times. Something is wrong with the Kubernetes cluster or API server, because that is what you're trying to hit with the r.update function, right? And then you can simply say, do you want, if you return an error, the reconciler will run again. That's usually, you can do that. It depends on how do you want to choose to build your operator. If I tried many times already, there is an error, I probably will just simply say nil, that I don't want my reconciler to exit and retry again because I just retried. I would rather send something as in send email because it is something bigger. You retried, then again, again, and again, and again. You couldn't update. Maybe the API server is no longer responsive. Someone needs to take a look into this. So here you can see what's being done. We will get rid of the is not found object, and here it's sending an email because something is bigger. So if you could retry, if you could retry, then we just ignore this. We don't want to do anything, because if you could retry, This auto control. All right. So in here, you were not able to update the object and you send an email. However, if everything goes fine, you could say successfully updated the object after the conflict. And because you changed the object, see, this is very important. Every time you make changes to your object, the reconciler remembers it. And when this one reconciler function exits, it sees that the object was updated, it will run again. And that's what we are saying. Because the update was done to the object, a new reconciler will be triggered and we exit gracefully without giving any errors, giving another run to the reconciler because the object was updated properly. If everything was fine, so this is the condition. If the error was something else, because you could have any other problems, this is where you can also control this. That fmt.println, there was an error other than the conflict. I'm going to return the error. Again, you could handle different cases. One of the case was if there was a conflict. You could handle other cases like if the object was not found, maybe it was deleted. That could be another reason why you might want to just not give an error. So you could say if errors dot is not found. If it's not found, then I don't want to do anything. If it's not found, I can't do anything, so I'm just returning gracefully. We are not complaining, we are not sending out an error from the reconciler, we are not telling Kubernetes try again, because the object does not exist, there's nothing to try. If we don't have the object, we try to update, we failed, what can we do? We can just simply ignore the failure. This is nothing that our operator can control. So you can have more than one conditions, and here also you can kind of like have a catch all for errors, and here you can say there was an error other than the conflict or is not found, and you just then in this case you really want to return an error and you really want to retry the whole loop for the reconciler, because you already have two cases covered. One of them was if it was not found, you do not do anything, nothing needs to be done. If it was a conflict, we retry. And if we couldn't retry properly, then also we send an email. We don't really run that again. But if we could update, if we could update our object, we simply say, yep, the update went through. When we retried, everything is fine. We don't need to rerun the reconciler because the object was already updated. And in the end, if there was no errors at all, you can see here, we just exit gracefully. So there are many reasons or many places you will find yourself. Do you want to return an error? Do you want to return gracefully? What do you want to do? Every place has its own value. In this case, we try to update, and if there was no error, we simply return because there was no error. Nothing needs to be done. If in case was there any error, that is when you are returning at different places and handling that error differently. But if there was no error in the first time, nothing needs to be done. We can just simply exit out of the reconciler and wait for a new object change detected by Kubernetes. So if I show you this in action now, I'm just going to clean this up a little bit. I don't want to look into is not found errors, and let's just do a go run main.go. I don't have any object right now that this operator would be looking into, so it's just going to wait, and I will do create. So as you can see, as soon as you create the object, the version is the object generation is 1, and the resource version is 80,748. It's going to wait because we ask it to wait. What I'm going to do is simulate that my object was changed outside. So I would say this is now changed, and you can then see its version or generation is 2. The version is also different. If I try again here, you see what happened? It found out that trying to update the object, there was a conflict error. and it tries to retry there right then and there. It did not exit the whole reconciler. What you are seeing this one is a new run because you update the object in here, and this is what it says. There was a conflict error, it was retrying, successfully updated object after retrying on conflict. Because update was to the object, a new reconciler will be triggered. And this again, it makes sense because you did update the object, and here you can see you got the latest version, and everything worked as expected. So this is something that you would be actually doing, and this is how you can make your operator more smarter in terms of not just retry, but how do you handle errors, because there could be errors when your operator, when your reconciler is running. So I think this is a bit longer video, but I really wanted to give you an idea of why would you want to do something, especially when you have multiple things juggling the same object at the same time. In case of when you have more than one operators trying to work on the object at one time, it's always a good idea whenever you are updating your object, whether it is a spec or a status, it's always a good idea to have a retry when you think that this object could be modified by some other controller. If it's not there, if your operator owns that object, nobody else is changing it, or no other process, no other controller is updating that particular object, you don't have to do that. There's no need to deal with it. But especially in systems where there are multiple actors running on the same object, it is a very good idea to implement this retry like we did so. And even then, it's a good idea to handle errors rather than just panicking and telling Kubernetes, please try again. I mean, rather than just returning an error and let Kubernetes do it, it's a good idea that you can do it on yourself right when you try to update. If there was an error, you handle that. If there was a conflict, you retry. Hey everyone, welcome to this video about operator best practices in the series. And today we are going to talk about how can you make your operator work a lot faster compared to what you might have been doing before. And for this, let's talk a little bit about what do I mean when I say make the operator work faster. Rather than saying we want to make our operator work faster, it should be we want to make our operator work in parallel. This best practice does not talk about how long does your operator take to perform an operation. By now, if you have been following the codes and if you have following, the best practices, you would be knowing that we always talk about this custom resource called EC2 instance, right? This is instance. There we go. Right. So we talk about a resource, a custom resource that we created in the course, which was EC2 instance, and our operator, which was running in this Kubernetes cluster, was responsible to reconcile on this particular object. It goes to AWS, it creates the instance, it gives you the information about that instance, such as the private IP, the name of that instance, the public IP that the VM has been given, and it essentially gives it back to you, and you update that to the status of your custom resource, and everything is happy. When I talk about making your operator faster, what we are not talking about is this process of delivering your customers the virtual machine, or whatever time it takes for you to do the task that your operator is supposed to do. In my case, if the time taken by my operator to talk to Amazon is maybe, let's say, 10 milliseconds, it makes a call to Amazon, then Amazon does its magic and gives me a virtual machine in 10 seconds. Let's say it takes 10 seconds for my VM to be really in the running and ready state. And essentially, then I get back my response another, say, 10 millisecond. This is not the time we are talking about to reduce this. This is something which is very um, programmatic. This is not how it is related to an operator. This is related to your own coding paradigms. Maybe you are using an inefficient call to Amazon, which takes longer. Maybe you're doing long polling. Again, it doesn't change the time it takes for the operation to work, but there are ways in which you can make your operations take less time. But that's not the feature of this video. What we want to talk about is when you develop an operator, you usually do this because there are people who want to use a product. Imagine this, that you are working in a company and there are people, there's one guy, there's another guy, and both of them, they are coming to you and they are saying that, hey, Shubham, they come to me and they say, hey, Shubham, can you please give me an EC2 instance? And I think about that maybe these guys would be, more benefited if I give them a self-service kind of portal. And that's where this is my Kubernetes cluster, where I create them a custom resource, which is again called the EC2 instance. I give them just enough data that they need to populate the custom resource with: the name, the service account that they want to use, the IAM role they want the EC2 instance to have, the private key they want in the instance to be added so they can SSH to the machine. And essentially, what would happen then? My operator will take this object. This is the operator, right? This is the operator. It will take this object, and this is going to create me an Amazon machine. And I would give it back to the user, whoever was requesting this virtual machine, and everything would be happy. The problem starts when you are growing in terms of the usage of your object. What do I mean by that? When you have one person asking for the instance, you have one operator and this is running, and that's fine. What happens when you have multiple people from different teams coming all to you and they say, hey, you know what, we need an instance as well. So there are 10 people. Imagine there are 10 people who submit a request for an object called EC2 instance. And then again, you have an operator that reacts on this. Essentially, what happens, you have a working queue. So you add 10 objects of kind EC2 instance, and then your operator reacts on top of that, and it goes ahead and it creates the virtual machine, create the VM. It gives it back to, it updates the status of this object. Then, after it has processed one out of these 10, this is interesting. You have 10 resources to create. You have one operator, and every operator has got something called a worker. And this worker is the one responsible to look into the queue and see how many objects do I have. If I have one, cool, I will take it. I will process that and I would move on. If I have 10, then also it does the same thing. It looks on the queue of your objects that are being updated. It takes one, it does not look at how many it has. It takes one, processes it, and it then moves on to the second operator object, then the third operator object, because it works as long as there are objects in this queue. It's gonna do that. But this happens sequentially. Imagine if here's a counter where there are some objects, you know and there's another counter. You need to move this object from here to this place, but you only have one person working, and this guy, even though there are multiple objects available on your left counter, he can only take one. Then he goes back and it places it on the right counter. Right, this is what your operator is doing. It keeps watching this particular slab, and it sees, oh, there are objects on top of that, but I can only carry one. at one time. And this is the reason why this happens is because your operator, when it is created, it only has one worker, right? So if somehow you can tell Kubernetes that, you know what, I assume my object is going to be used a lot. I assume that there are going to be many people trying to make changes to my object, trying to delete that, trying to create that. I don't want just one person who's doing the lifting. I might need multiple. And that's where you can tell Kubernetes operators, which is we are using Kubebuilder as a framework, you can tell Kubebuilder that please go ahead and create me maybe two workers or three workers or four workers. Essentially, there's no limit to how many workers you can create. I mean, there's always a limit because every worker consumes compute and memory. So you don't want your operator to be using gigabytes of memory and cores of CPU. You don't want like more workers than the requirement because it doesn't make sense. It's not a right optimization. But you would be increasing the number of workers, right? And this is something you can do in your operator itself. In the reconciler, where you run your operator manager, that's something where we can configure this. But let's look at that in action. How does it look like when I have 10 instances and I only have one worker? How long does it take for my operator to be working? So this is the code that you have been looking at in every video, and you should be very familiar with that. This is our reconciler function. If I quickly show you the API that we created, it was EC2 instances, and here you can see every object has got the metadata, it has got the object metadata, the type meta, and then it has the spec, and also it has the status. It's fairly simple. There's no magic going on. We only have two keys. One of them is foo, the other one is bar. We don't have anything in our status because that's not something where we are looking forward in this video. Now the controller here is also very simple. This is a reconcile function, and this reconcile function is the one that is running every time your object gets updated or created. The object in this case is the EC2 instance custom resource that we are working with. So what we do is we register the time at which my operator started, and we're just printing it so we have a bit more verbosity that the time it was started was time dot now. So this is the start time of the operator, the start time of the operator. Let's say not the operator, but the reconciler. That makes more sense. The reconciliation and right. So we print out that we started our reconciliation at this time, and we create a variable of type EC2 instance. This is nothing new. You have been seeing me doing this for a very long time. If you have been following along on the videos for operators, we create a variable of type EC2 instance, which you can see it only has a spec and it has a status. The spec only has two things, foo and bar. We get the object from the reconciler request because whenever your object gets updated, a request is sent to your reconciler. So we use the reconciler and the get function to get the object which is of type which is coming from the request. We get the namespace name. Essentially we get two things from this. We get the name and the object, the namespace and the object name from the request. We store that into our EC2 instance, and here's where you will be simulating a task that takes 5 seconds, for example, to complete. Think of this as creating an EC2 instance on Amazon, right? So I'm using Cursor, which is pretty good in terms of helping you with the development. But imagine each object that your people are working with, that your customers are using, it takes around 5 seconds to complete. right? Around 5 seconds. I'm not saying exactly five, but let's say for to keep it simple for the video, we say anytime someone creates an object which is of kind EC2 instance, this will create an Amazon machine, and this particular operation takes 5 seconds. Now, let's try to do this. Let's try to run this, and then we are just very simply printing that the total time taken by the reconciliation is we get the time dot since from. I think it makes sense to have it as a variable because we want to store the time rather than calculating it here because it will be zero because time since now is nothing. It's zero. So let's do that start time, and essentially that is what we wanted to do. So we very simply print out the time it has taken since the starting of our reconciler, and then we return because we are not really making any changes. We are just saying how the reconciler function, how the operator works if we change some object. And here's a same setup with manager because we have an operator manager and we set up our reconciler with that manager. This is something which is pretty standard. And if I show you the object that we're going to work with, this would be something in config sample, and here you go. So you can see this is kind of how I'm simulating that multiple people are trying to interact with my resource. So this could be a person from team A who gives the object that I want to create an EC2 instance. This could be from team B, team C, team D, team E. Could be multiple files, could be same file. The only important thing is all of these objects that I'm giving to my Kubernetes cluster at the same time is because this is how people would be using your object. There may be two people, three people, four people in a team who would be trying to talk to your operator at the same time. No, the only thing difference is the names are not clashing because we don't want to keep the names clashing because this is not a namespace resource. If I have instance one, if I try to create that again, I'm going to get a problem that you're trying to create a resource which is already existing. We don't want that. Kubernetes 101. And here you can see instance two, and here you can see three, and the same four, and it's five. They have different names, they have different data. The data could be anything, it could be the same, it doesn't really matter, but the name should be unique because it's not a namespace scope object. What I'm trying to do here is just trying to see or trying to tell you is there would be, imagine this is being done by different people, right? So let's run our operator. I will see first if I have any EC2 instances in my cluster. I do have one. I will delete that. Um, I will delete that and I will just install my custom resource definition again because I was working on multiple versions of the operator, but this is the one that I want to use. And I'm using vCluster platform to run my local development environment. So I could say go run main.go. So this is running our operator. And that's where you will see this line, which is very important. It is starting the controller, it is then starting your worker, and you only have one worker for the controller kind of EC2 instance. That means if someone creates an EC2 instance, even if they give like 10 instances, which is what I'm doing in this example, it is only going to have it is only going to create one instance at one time. And this is exactly what you want. See, the thing is, you do not want more than one people. So imagine this that this guy called A and this is called B. If A was already working on this object, if A was already trying to move it to destination, you don't want B to interact with him, right? This is the same thing that happens when in cricket you have a cricket ball and there are two people trying to catch that ball and they just collide into each other and the catch drops, right? You don't want that. What you want is If there were two balls, which in cricket is not a good example, but if there are two balls, each one should be only looking at their ball at the same time, because you don't want either of the balls to be dropped on the ground. That is what we want. We want to make our operator faster so that, not in terms of how long does it take to create the VM, but how long does it take for the operator to react on those 10 available objects. So we only have one worker, you can see, and I'm going to create all these five instances, and you will see how this is behaving. So if I do create, you can see here, start time of the reconciliation is this, and you see, I created five instances, but what's happening is it's being done one by one. And the operator is smart. The workers are smart. They know that there were five instances that were changed. I need to work on five instances, but I can only take one at a time. I cannot take multiple at one time. And you don't also want that. So you see, what's happening is every time the reconciler starts, it calculates, it prints out the time, and it prints out the time taken for that reconciliation. Every time the reconciler runs, it runs because an object was updated, it runs because an object was changed. You would be, if you were thinking that every time, you see, I'm taking 5 seconds for one instance, I have five instances, my reconciler will take 25 seconds for all five. That's not how it works. Yes, for my loop to run, if you will just count them five, 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 five times, it essentially took 25 seconds. But one worker takes 5 seconds, um, and five times is when it's added to 25. It doesn't change the time taken per reconciliation. It still takes 5 seconds for one object. Now, what you can do in this case is imagine if the time taken was longer. If your operator takes more time, let's say 2 minutes, or which is not too bad, but it's not also not great, not terrible. Quoting Chernobyl here. However, let's kick things up a notch, and I would say, it doesn't sleep for 1 second; it sleeps for 10 seconds. Every time you are going to, because I'm creating five instances, so just trying to simulate that now it takes 10 seconds for each object, and I've got five, so I'm just printing it five times. So it's going to be actually 50 seconds, which is not what we want. I want 2 into 10. So five times it's going to run 2 seconds, so 10 seconds in total is what it's waiting for. If you stop it and if I run that again, you're going to see the same thing. See, now, for each instance, it hasn't even started on the other instances yet. It's just using instance number one. Then it moves on to instance number two. This is a serial um, work of your operator on your resources, because you only have one worker. The worker is busy here with instance one, then it moves on to instance two, then on to three. People who have created their object before the others, it, it's going to be given priority to them. Actually, this doesn't make sense, because it is not really 1 2 3 4. It's not by the creation timestamp. But the thing is, your worker is using one object at one time, and this is not what an efficient use of the operator framework is. You could say that in my company, I see a lot more usage. So if I have like 10 objects, it makes sense to create three or four workers, because then they can have things in parallel. They will still be completely separate from each other. If I give 10 EC2 instances, they're going to be creating 10 different instances, completely separated, because they do not work with each other. All they do is they grab an object and they do what they have been told to do separately, without working with other worker processes. And this single thing can really help you um, to work with your operators much more efficiently. And that can be done in the setup with manager function. What you can do is you could say that for the EC2 instance, that is what my operator should be reacting on. I want it to react with the options, and then you have options within your controller. And here's you can see there are options, and one option is max recurrent reconcilers. Reconciles. That means it's essentially a fancy word for number of workers. How many maximum um, instances of the reconciler you can run? And because we know that one worker runs one reconciler at one time, if you have 10, then there will be 10 workers. They can reconcile 10 times, or they can run this function at one time 10 times. And that bit is going to make huge difference for you. Let me put it back to where it was for 1 second, right? Because we wanted it to be 1 second. And now you can see how it works as a difference. What difference does it make when we run this again? Now you can see I run my operator, and because I now have 10 workers, you can see it's already doing things in parallel. I'm starting with a reconciliation time, and you can see this is instance 2, 3, 2, 5. It all, each of them took 5 seconds because we are not reducing the time it takes individually, but your other objects that were there, they are not waiting to be picked up by an operator, because your operator has number of workers which are all busy. They will be taking up the object when it's free. We don't want that. Think of this practice as when you have a lot of use for your custom resource. For example, pods. If I was to create 100 pods and only one could be created at one time, you're going to be waiting before your pod could even be scheduled on a node, before it was even picked by the operator. So number of workers increasing, that it really helps your operator being a lot more parallel. It helps you to pick those objects much faster, and essentially then whatever time it's going to take, they will, because we can't stop that. As I said, if they're going to take 5 seconds in each iteration for each object, they will do that. That's not the point of the video. You could do this by saying, okay, if I wanted to reduce the time they take within each reconciler for each worker, I could say millisecond. This is, I make my program more efficient, and they're going to now take 1 millisecond. But the point is, if you have a lot of if you have a lot of objects that you're working with, and you do not want to wait for them to at least be picked up and get started, because imagine this case, this is for humans, that let's say on an axis of time, here time being 0 and here time being infinity, if creation of one instance, right? If creation of one instance takes 10 minutes. I'm just giving you a very simple example. If this takes 10 minutes, it's bad. Again, it depends on what you're trying to create and where you're trying to create that. But let's say this one is 1 p.m. So 1300 hours is here, and then there's probably like 2300. If I was to start my operator creation from 1300, I would be getting my instance at 1310, because it takes 10 minutes for my instance to be created. However, if there's a flood of objects, right? If you give like 10 objects and each one takes 10 minutes, so your instance, which was probably taken the last, it would be starting 10 minutes, 10 minutes, 10 minutes, 10 minutes, 10, 10, 10, 10, 10, and then here. You would be starting, your request would even be picked up after like, it takes one instance, 10 minutes, or 100 minutes. So after an hour, or more than an hour, more than 1.5 hour later, your instance request would be picked up. So it would be around 14 um, would be about 14:30, 90 minutes, or 100 minutes would be. So 14:40 is when your instance would be picked up. But you made the request at 1 p.m. you requested, and your request was started to be picked up at 2 hour 40 minutes and PM. And then you would get your instance in the same 10 minutes, because everyone got their instances in 10 minutes, but you had to wait because there were only one worker. If only you have like 10 workers, and if only you have 10 objects, all these objects would be picked up at the same time. They would be worked on by one worker, and you would get your object. All of you who have requested for the object, they will be getting their object after like 10 minutes, because it takes 10 minutes to create one instance. The whole idea is, yes, there are ways in which you can make your reconciler efficient, which is what I did, from time second to time millisecond. That's always possible. Again, it depends how you have coded. But the the main motive of this video is to make your operator behave in parallelism. So you as a user are not waiting for someone to be free and pick up your request and start working on top of that. And that could be done with the controller options, using the max current reconcile. That means, how many concurrent instances of this reconcile function could be running. And because one worker will only work on one object, if you have 10, you could give 10. There's no limit to how many workers you can have. Of course, it's also a bad design if you have like 100 workers, but only at a time you get 5 requests, 10 requests, 10 object changes, creations on your custom resource. That's also a bad decision. There's no one stopping you from doing that, but you wouldn't be making 100 rooms for people, who are only maximum 10 at one time. So the decisions like these would actually help you to make your operators much more faster in terms of parallelism, right? And that's the object. That's the objective of this video. If I would run that again, now you can see it's efficient in terms of how long does it take for the instance creation. It's like 5 milliseconds, but it still picked up all of your instances at parallel, because you now have the worker count to be 10. Small things like this can really make a difference when you are using your object, when you're using your operator at scale. All right. So, for this best practice, before I talk about what we are going to do here, I rather want to draw a picture. So, if you have gone through my previous course of how to build your own Kubernetes operator from scratch, you must have heard me saying this many, many times, that every time you make an update to your object, you are triggering a reconciler loop. And I've said this extensively in the video. You run the reconciler loop again, and this is why you need to make things idempotent, so that if the external state that your object is managing, or your operator is managing, if it matches the desired state that the user has asked for, you simply do not do anything. Think about Ansible in this case. You write a playbook that installs a server, that installs an Nginx application server on a Linux machine. It starts the service, and you run that again. It does not reinstall Nginx. It does not restart the service. It just simply says things are exactly how you want me to make, and I'm not going to make any changes. The same thing happens in your reconciler. So any update that you are making, whether it was an AI, tool that did it for you, whether you did this with kubectl, or whether it was GitOps that makes the changes, for whatever reason, there's an update to your object. An object has two fields, which is spec and the status. Either one that you update, this triggers a new reconciler loop. And this is why your reconciler should be idempotent. that if no change is needed, I do not do anything. I have talked about this extensively in the YouTube video where we talk about how do you build an operator from scratch, and I would be putting a link of that in the description. Now let me draw a picture. We made an EC2 operator. That operator creates an instance for you. So in that operator, we had an object, and we had a simple spec, things that you need when you are creating um, an instance, which is with in Amazon. So, so you had basic things like you had the instance name that you want, the AMI ID that you wanted to use. You also had then the security group. You then talked about the storage that you want to use. Um, and you could be as descriptive or as, options you can give as you want. But I'm just going to keep these simple. This was the spec. And the status had a couple of fields like the public IP. What is the public IP of my instance? And it could be the creation timestamp. Now, these things you will get or you will, use to create an Amazon instance. And here is your EC2 instance. Now, imagine you wanted to make this operator a bit more reliable, or you wanted to make this operator a bit more intelligent. What you thought of is I have the public IP, I have the creation timestamp. I want to periodically check if my instance is there or not to do some sort of drift detection. And you wanted the user to know when the last check was made. So you introduce a new field in the status. See, you're not changing the instance. You're not changing the instance's name. You're not changing its AMI ID. You're not changing anything on the instance. Nothing is being changed. The spec is exactly the same. What you are changing, or rather introducing a new field, which is called last checked at. All you have made in your operator is it goes to Amazon with that instance's name, see if this instance is there. If it's there, it does nothing. It only updates your reconciler. It does not do anything if it's there and running, because that's what you want. This is your desired state. If it's not running, you can start it. If it's deleted, you can maybe send an email from your reconciler. That's all you can do when it's not there. But if it's there, all you wanted to do is to update your status of last check that. And this could be, 5 p.m., 5 p.m., 10 minutes, and 20 seconds. This is when you made the change. And you want to do this periodically. Every 2 minutes, let's say you want to make a check on Amazon that if the instance is there. So every 2 minutes, your reconciler is running, not doing anything on the spec because you don't want to change anything on the spec, but it goes ahead and checks it checks your instance. And every 2 minutes, it's updating this specification here, which is last check that. The thing is, you are updating the status. The resource is already in that state. Now, what's kind of happening is what I told you, that when you make an update to your object, it triggers a reconciler loop. We talked about this. And if you are making changes to your object in the reconciler loop, you will be rerunning. You may update the object, the reconciler loop runs, you update the object, the reconciler loop runs. It does not matter if the object was updated externally from someone who's using kubectl manually, or it was updated in the reconciler loop itself within the reconciler. The only thing Kubernetes cares about, object was changed, I will rerun the reconciler loop. which is then you have the steps for creating the instance. Then you have, maybe sending an email to the team with the instance IP address, um, and all of the steps that you need to do when you are creating an EC2 instance. The problem is these steps should only be running when you actually want to make a change, whether it is creating a new instance, which is in this case, it just creates an instance. Just because you updated your object, or I should say, just because you updated your status that the instance was there, you need not to run the whole reconciler loop. You should run the reconciler loop again if I change the AMI ID. In that case, your operator should, delete the instance and recreate that again. You need to make some changes in the environment. But if I just go ahead and check, hey, if the instance is there, if it's there, I just want to update the metadata. I did not change the name of the instance. I did not change the AMI ID of the instance. No security groups are changed. I didn't increase the storage from 50 to 100 gigs. Nothing is changing. So why are you running your reconciler loop and wasting your precious CPU cycles? This is where you are trapped in a loop where you update the status, which was supposed to be the metadata, the reconciler runs again. And this loop continues forever. So this is what I kind of wanted to show you. When you are creating the instance, you have a spec here, and then you have the status, which is where we have the last check that. Your operator goes to Amazon, sees if the instance is there. If it's there, we don't make changes to the spec, but we make changes to the status where we update it with the last check that and the time. The thing that happens is because you updated your object, there was a watch event which your operator always watches on, your controller always watches on the operator. What am I saying? Your controller always watches on the object that is changed and you rerun again. Even though you did not really want to make any change, your reconciler logic should have just skipped it that, hey, you know what, guys? The user did not ask me to make any changes to the VM. Why am I even running? Okay, I know I have to be idempotent so that if I run, I should not make any changes. But why run in the first place? If I was not, changing the spec, if the user did not change the spec, there's no reason for me to run. The change was only at a status level, which was only the metadata. And this is the problem with the reconciler, or not the problem, but the way the reconcilers are created, because Kubernetes does not differentiate if the change was in the spec, which you most care about, or was it in the status, which you care about less to rerun your reconciler. It only says the object was updated, rerun the reconciler loop. That's it. So I hope you got the problem. You're updating the status of the object, and this triggers an update, and this triggers a reconciler. And within the reconciler, you updated the status. You then got an update event. The reconciler runs again. You again go update the status. You then Kubernetes says, hey, an update is there. The reconciler runs, and this is going to make your operator a living hell. Yes. I mean, see, the thing is, you could say, Shubham, it's not a problem. Even if even if my reconciler runs, you told me to make it idempotent. So even if it runs, nothing's going to be changed in my Amazon instance. And that is correct. But that's the difference between you and a staff engineer or a principal engineer who would stop you from running that operator even in the first place, because you're going to be using CPU of your cluster. And if you do not design things properly, you could eventually, waste your resources. So this is what we have been doing. So the user, he makes a change to the API server. There's a component in your operator which is called a reflector. And this reflector is responsible to watch your object. We're not going to go into details of what and how reflectors are implemented. Think about this: the reflector is the one responsible to keep an eye on your object in the API server, and it catches these events. It's the one that updates the informer. So you go ahead and you update the cache with the latest object that was updated by the user. And then the event handler is the one responsible to add it to the working queue, where you add what object has been changed. And the reconciler gets the object from this cache. So it doesn't go to the API server to get it. And what it does is it does an update of the status. Eventually, here's where the loop gets created, which I just showed you above. That's the loop that you're making. We're just going into a bit more detail here. So every time you make a change to the object, the reflector gets it. The reflector sees that there was a change. The reflector talks to the informer, which gets the object and stores it into the cache memory or the cache of the operator. Then the event handler is informed that, hey, you know what, this object has been changed, please add it to the working queue. And the reconciler workers are looking at the working queue, seeing that new object has been changed, it has been added to the working queue. I need to start and run my reconciler. Then in the reconciler you update the status, and this whole story, the whole story goes on. I think it makes more sense if I show this to you in a demo. So let me go to my trusted cursor and let me show you how this looks like. So this is standard Kubebuilder. I'm sure you have gone through the video, so you are familiar with how the how the Kubebuilder structure looks like. The most important things that I wanted to show you is my API, and this is what I have created. So I have a very simple new custom resource called EC2 instance. It has two things. It has a spec of type EC2 instance spec, and then it has a status of type EC2 instance status. Now the spec is very simple. It's just foo and bar. It is just the two foo and bar keys that I want to use. We're not creating a fully functional operator in this video. We did this in a previous course. This is a continuation from that course. The status is what we are more interested in. And here's we have the last updated at, which is a type of metav1.microtime. This is a struct that lets you add a time up to microseconds. We will talk about that. And this is my simple EC2 instance custom resource. It just has a spec of foo and bar and the status, which is last updated at. Now, how does my reconciler look? So if I go to my reconciler here, you can see there are a couple of things that I do not need. I don't need the math library as well. So here's my reconciler. See, this reconciler does something very, very simple. It does something very simple. It gets it creates a variable of type EC2 instance. So this is where we will be storing the object that we get from Kubernetes in this line here. This code is something that I've already explained extensively into our Kubernetes operator video. So I'm just going to go through that very quickly and show you essentially what's happening. We create a variable of type EC2 instance, which is our struct, which is our custom resource. We get the object from the request that was made to my reconciler. API server said, hello, this object has been updated. I get the object, I stored this into a variable, and I'm reading that variable as such. So foo value is instance.spec.foo, and bar value is instance.spec.bar. Now you can see here, so far, I've just got the object and iterated over its values. Now here's where the interesting thing, here's where things gets interesting. What I wanted to make is I wanted to do an update. See, I have this EC2 instance custom resource. It has two fields, spec and a status. I am only reading on the spec. I did not make any changes on the spec. What I'm making a change on is the status and the field called last updated at. So I want to set the last updated as field to the current time to the microseconds of the current time. And this is where we get the time in UTC, and then we convert that, or rather we format it into a time which is microseconds. I think it shows microseconds, and then I'm doing a status.update function. What this does, this line here updates your object. So essentially what's happening is you start your reconciler, you get the object. Okay, here's where you got the object, here's you got the time, and then here's where you read, or they could be interchanged, but that's not something we need to worry about. What's essentially happening here is where you update the status. And because you updated the status with the r.status.update function, you're going to put this back to the working queue. Work queue. Think of this working queue as a place where once your reconciler is done, he goes and sees, is there something? And yes, you added your object key, the name of the object that was updated here. Now what's going to happen? You update the status, and then we are printing this function. Last update is, you print something that last update is done, blah, blah, blah. And then you return. Now, as soon as you do a return, your operator is going to look in the working queue. He's going to read from the queue, and this is going to write to the queue, which is the name of the object that was updated. You read it, you rerun the whole reconciler from the beginning, and here you see you update it again, you write it, you finish, you go back to the working queue, you run from the beginning, you read it, you write it. This is the loop that I've been talking about. And let me show you this in action. So here you can see we have, so there is no EC2 instances right now. I have already installed this in my cluster using Kubebuilder, and you can simply use the make generate, make manifest, and make install. I've just done a clean installation, so I'm always using uninstall and install because I was making changes to my spec, my status, but it's installed, so you can do kubectl explain ec2 instance.status, and here you can see the status field has last updated at, and spec has got bar and foo, which is exactly the spec that we are creating. All of my terminals are connected to the same cluster where we have installed these custom resource definitions. Now, if I wanted to show you what we are creating, you can see here, it's a very simple EC2 instance. It just has a bar for testing. It has foo for testing. Nothing fancy. So I'll run my operator, and because there is no EC2 resource, there's no EC2 instance of custom resource, it's just watching. It just says, okay, I'm waiting for any changes to happen on your operator, on your custom resource, whether you update it or you create that. Now I'm going to create this in my cluster, and you're going to see something interesting, which I've been trying to show you. Let's create that, and you see what's happening. You see, my operator is going crazy. It's running and running. And here you can see the status update is happening, which I wanted this, but my operator keeps on running. My reconciler has gone crazy. It's gone into a loop where it runs, it updates the status, then It registers in the working queue, it exits, sees in the working queue, runs it again, updates the status, puts it into a working queue, exits, sees the working queue, and this is the whole shenanigan that's been going through. And this is something you absolutely do not want. You don't want to rerun your reconciler just because you made a metadata change, which is the status. Why would you want to do that? Now, something that I also want to, put into here is something called generation. See, as your operator is making changes to your resources, you do update the last update at because this is what you want to do. But Kubernetes also updates something called a resource version. This is the version of the resource which was there in HCD. So you always have a resource version which is telling you the latest version that your operator is in HCD. There's also something called generation. Now you can see my operator has been running for so long, and I've got about so many resource version changes. However, I only have generation as one. Now let me show you something really interesting. If I stop my operator and I do kubectl edit EC2 instances, I do a bar and I say new testing data. I save and quit that. See what happens? The generation changes. This time, not just with the resource version changes anytime you make an object change, but generation changes only when you update the spec of Kubernetes, of your object, not the status, because we kept running our operator for a very long time, which is you can see again, you can see here, my status is changing, my resource version changes, but the generation never changes. However, as soon as I do a change, in this case, I do foo testing, you see, my generation is incremented by 1. So every time you update your status, the generation does not change. But every time you update your spec, the generation is incremented. And that's something you can make use of when you are writing your operators to not go into this forever running loop where you update the object, then you read, you update the status, you rerun, and getting yourself throwing those precious CPU cycles away. And here's what's going to happen. See, when you are working with status updates, you just see there was a change. You don't care about if the change was in status. You don't care about if the change was in spec. Or Kubernetes does not do that. Your operator does not care about it right now. However, in Kubebuilder, in controller runtime, there is an option where you can say, guys, I only want to trigger a rerun of my reconciler if the generation was changed. That means if the spec was changed. You always want to rerun if the spec has changed, because when you change the spec, that is generally to reflect the state that you want in here. If I, let's say, think about this. If I have a deployment and this creates me, it has spec dot template dot spec. It has replicas. If I have 5 replicas, I'm going to get 5 pods. If I change this to 10, I need to take an action, which is incrementing to 5 more pods. So I need to do something externally. I mean, not external to Kubernetes in this case, but you want to make some changes. In case you want to add a new environment variable, you need to rerun your pods because the environment variable has been added there. Or you change the value to the environment variable, the pods have to be recreated. Some change has to happen, whether it is recreating the pods, whether it is recreating the config map, whatever it is. You need to react on that change. But if you update the status, you do not need to react Many of the times, you do not need to react on these updates of the status. And this is exactly what you're gonna be in a problem. And the solution for that is to better manage your status updates. So the same flow continues. Somebody makes changes, user or your own operator makes changes via the API server to the object. You get storing this into etcd. From there, the reflector watches this event, it gets the data, gives it to the informer, and you store that into your cache. Now, because the operator was updated, your reconciler has to run. Now, what happens is you give it to the event handler, which again was responsible to add this object into the queue. But now you have a predicate filter. You're making your operator a bit more smarter. What you say, hey, event handler, I want you to add this into the working queue only if there was a change in the spec, not if there was a change on the status. So I want you to ignore the noise, or I want you to simply skip running the reconciler, or rather, one step further, I don't want you to be putting this object into the working queue, because once it gets into the working queue, your reconciler will take and run. So you're simply telling with this predicate that, guys, I only care about the changes in the spec. I do not care about the changes in the status. That means if the generation was changed, then do your thing. If the generation did not change, do not rerun that again. And there are some other predicates as well. The one we are talking about is the generation changed predicate. It simply checks if the generation has changed. That means the spec has changed. That means I want to run it. But if the generation did not change, that means the spec did not change. Probably it was just a status update and do nothing. And that line, that one single configuration, is going to stop you from wasting your precious cycles, your CPU cycles, because um, you don't want to just write an operator as a junior engineer. You want to write an operator thinking it's not just running, it is running efficiently. Because if you really go into operators, you want to keep them as efficient as possible. Otherwise, your resources are going to be wasted on the operators themselves rather than the data that they are managing. So you have to be not careful but smart about it this time. That's why it's called a best practice. So how do you work with that? And here's where the magic happens. When you are setting up your controller with your manager, I think, let me just quickly talk about that. You have a manager, and within a manager, you can have multiple APIs. Usually, you have an API, and for that, you have a controller. The same thing happens here. Let me copy that here, and let me copy this. So you can make multiple APIs with Kubebuilder in the same project. For example, I could have my Kubebuilder domain as cloud.com, and I can have APIs as EC2 instance dot cloud.com. I can have one object is EC2 instance. I can have, so this is going to be my API number one here. So one controller that manages the EC2 instance for me. The other one manages buckets. So buckets.cloud.com. The other one could be storage, or it could be, ebs.storage.cloud.com. And then you can have efs.storage.cloud.com. You can make multiple. The thing is, all of these controllers have to be registered with the manager. This manager is responsible for running multiple workers, threads, routines, for your controllers. So this is the one which is doing the heavy lifting. We attach our controller to the manager using this function, setup with manager. We define which manager we want to use. And essentially, we are telling that for this object, for this object, I want you to attach this to my manager. I want you to do this with an event filter. And here's the one that is going to make your life a lot more easier. So what you're telling is, I want to filter on some events. Previously, you were just updating you were updating my working queue, even if it was a spec change or either it was a status change. But this time, I don't want you to do that. I want you to see if that was a spec change. I want you to see if the generation has changed. Then add this to my working queue. If it hasn't changed, then don't do that. Do not add it to the working queue. Do not let my reconciler rerun, even if it's idempotent. Don't do that. Think about this. You have an Ansible playbook that has like 100 tasks, and you followed the best practices. Your playbook is top notch, it is idempotent and all good. But why would you even want to run this in the first place if there was no need? If no need, don't run it. If it runs, it doesn't change. Okay, that's a good argument. But the better argument is, if not needed, do not run it. Because even if you run it, even if no changes were made, you're wasting your compute. And that's what we want to stop. So with this event filter, we have a couple of predicates available. And this generation change predicate simply says, if your generation did not change, don't do anything. So here is what you can see. Now if I run my controller, the first time my controller runs, it will update the status because I want my status to be updated. The next time, because there was a loop you saw before, the next time we are, our controller is going to see, hey, you know what? The generation did not change. That change was only in the status. So I'm not going to rerun that. I'll just wait. So let's do that. Now, I hope this is going to work just as we want it. You see, we did update our last updated at, but that's it. Our operator is active, is running, but not doing anything because of this one predicate, because my generation did not change. If I want to show you that again, you see, right now our microseconds is 108. Just to show you that the changes are actually being made. This is what we have currently right now. And if I rerun my operator, this will be updated. So you can see here, now the time has changed, the status has been updated, but now see what happened. It's here. So see what happened. You updated your object. Okay, you updated your object. You updated this into the cache. You have stored this into the cache. Then the event handler, before it added this back to the working queue, it saw that the generation has actually not changed. And that's why it did not add it back to the working queue and the reconciler did not run. Even though the reconciler did update the status, but it did not do anything at all apart from that. And that's what we wanted to do. We wanted to light our operators so that they do care about spec, but they do not care much about the changes on the status. This lets you have a free hand of any sort of metadata that you want to put into your status. You want it to be more descriptive. You want to have more fields in the status to make it as more descriptive as possible. But you were worrying, or you were managing, how do I not rerun my reconciler if I'm doing a status change? I have to be very careful, but this one single predicate does it for you. It says, if no change in the generation, I'm not going to rerun that again.
It did run the first time. You see, we did read the value of it. And here is my update. So this is what I wanted to show you, how the generation works, how the resource version works, and especially the generation was changed when you update the spec in Kubernetes. The generation does not change when you change the status of your operator in Kubernetes. So I hope this has been really helpful, and this is going to help you create operators better. Not create operators, because that's the course that helps you to do this, but this is going to help you write operators thinking from a point of view of a platform engineer who's not just a junior, but a staff engineer or a principal engineer. These things are really mattering when you write operators, and this is how you should write this in a better way. So I hope this has been useful. If you have any questions, let me know in the comments, and I will be happy to answer your questions, and I will see you in the next video.